This is the video for the first subunit of oxidation and reduction. Of course, you remember that oxidation is the loss of electrons and reduction is the gain of electrons. And we used our example, the formation of sodium chloride. We can see that this is an oxidation-reduction reaction by writing it out as half equations. First, we can see that each sodium atom is about to lose one electron. Second, each chlorine atom is about to gain one electron. This, of course, leads to the ionic bonding of 2 units of sodium chloride. Chlorine was reduced while sodium was oxidized. Chlorine was the oxidation agent of sodium and vice versa. Alternatively, we could express it as chlorine oxidized sodium while sodium reduced chlorine. We can also analyze this redox reaction by assigning oxidation numbers. Here, everything is in its elemental state, so that means it has an oxidation number of 0. By the end of the reaction, the oxidation numbers have changed. The chlorine has a -1 and sodium has a +1, the same as their charges. There are some common oxidation states we need to remember. Many elements, such as the group 1, will form the same oxidation number as their common ion. Fluorine pretty much always have a -1 oxidation state. Oxygen also follows its pattern. However, there's a few important exceptions, namely peroxides and oxygen difluoride. Hydrogen will usually have a +1 oxidation state, except in the case where it's in a metal hydride. Chlorine is usually a -1, except when combined with oxygen or fluorine, the only 2 elements that are more electronegative than it. In order to assign oxidation numbers, we need to keep in mind some guidelines. If a species is in its elemental state, then all atoms involved get an oxidation number of 0. In simple ions, that is, ions made of one atom, the oxidation number is equal to the ion's charge. In neutral compounds, all the individual atoms in that compound, their oxidation numbers have to sum up to 0. And in a polyatomic ion, all individual member atoms' oxidation numbers need to sum up to the charge of the total polyatomic ion. We can assign the oxidation numbers in 2 major steps. First, we should assign the oxidation numbers for elements that have very common oxidation states, such as oxygen, hydrogen, fluorine, and chlorine. Last, we should assign the oxidation numbers for elements that often have different oxidation states in different compounds, such as nitrogen, phosphorus, sulfur, tin, lead, and all the transition metals. So let's work through an example. How about the formation of water? First, we should assign our oxidation states. Hydrogen and oxygen are in their elemental state, so every atom gets an oxidation number of 0. After the reaction is completed, oxygen has its usual oxidation state of -2, and hydrogen has its usual oxidation state of +1. Notice that for each molecule of water, the oxidation states add up to 0, because water is a neutral molecule. The formation of water is highly exothermic. In fact, this is what powered the main rocket engines on the space shuttle. It really shouldn't surprise us, because this is a combustion reaction. We have a fuel, hydrogen gas, combined with an oxidizer, in this case, oxygen itself. When an element has different oxidation numbers in different compounds, we use those oxidation numbers inside the systematic name for those compounds. For example, here we have 2 iron oxide compounds with different formulas. The different formulas, in each compound, iron has a different oxidation state. And so we use that state in the name, such as iron 2 oxide and iron 3 oxide. Here's an example with copper in 2 different oxidation states with oxygen. And we can do the same thing with magnesium and oxygen, or even chromium in a more complicated compound. That's it. Thank you.